Wow. Wonderful. Do you guys have any questions or concerns at this point? We're starting our last chapter of before the exam, so we've covered 3 others. I just want to pause a moment. And say again? Yeah, it is next Monday. I have the calendar here. Right, good. It's always good to make, before I tell you what I was thinking, it's confirm that, yes, that's what I wrote. So today and Wednesday are chapter 35 on the special theory of relativity. Friday we'll review, and so the exam will be in a week, next Monday. While I'm on that, though, this will be different. Are you listening? Homework won't be due Sunday. It will be due Friday before class. It says so on WebAssign, but that's different, so it might be throwing you off. Reason being I do that is because the way it works out, we're having the test Monday. If I had the homework due Sunday night, you'd have less than a half a day to go back and see solutions to homework 35. So I'm going to have homework 35 due right before class Friday, so you'll have the weekend to look it over. We'll be done covering that material by then. Obviously, you could have started back after last Sunday. Well, yeah, now. So you have all week until Friday. And here's a question over here. Yeah, you have. Do I have access to it? Was that the question?
Yeah, I was just asking if it was indeed on chapter 35.
Yes. Yeah. You just finished homework on 7 and 10.
Yeah.
So this one's just on 35. And I didn't ask as many questions as you normally have. If that makes you feel any better. Anything else? Things that have been bothering you that you wish you understood a little better, or questions you're going over, things in the text that didn't make sense, things you observed in everyday life? Just give you a chance. Relatively speaking, I've had less people contact me outside of class. And our TA, remember our TA? His office hours and locations listed in the announcements on WebAssign. Last time I saw him, told me nobody's come to visit him. He's available as well. Granted, if you don't need our help, awesome. But I'm just reminding you that you have those as resources. And I don't remember off the top of my head what his office hours are. I posted them on WebAssign. And please don't show this. This is on my site anyway. All right, load that page. WebAssign, announcements. There it is. Muhammad, his office hours are Monday and Wednesday from 2 to 3. And in case that didn't work, he made it different on Fridays from 4 to 5. And his office is this building, 209. Desk 12. There's several students in there. And me, of course, just contact me. We'll find a time. Or you can just email me questions or whatnot. But anyway, that's our TA's info. Anything else? Yes? Something's moving and things are dropped. So the airplane question, right? Yeah, I'll use the homework one. The airplane's moving along, has a horizontal velocity, and it lets go of a package. So where does the package land? If I'm bad example, but we'll use the rag. You're cruising along, and you let go of it. Here, I'm going to try to let go of it right in the middle. Where do you think it'll land? Who thinks it'll land here? Who thinks it'll land further? Who thinks it'll land behind then? Half of you aren't playing. Could be on the test. I'm walking along. It's like an airplane. Drop a package right here. I'm going to keep moving. I mean, you got right now 3 options. This side, right here, or over here. Who thinks it'll land over here? Here? A couple of you. Hey, over here. All right. Most of you are still playing. The rest. Yes, I'll give you. It's going to go this way. But now, where will it be in relation to me? I let go of it back here. I keep moving. Will it land behind me, at me, or in front of me? Behind? At. In front? You're right. At me. So let's discuss the why. At least we're all on the same page. You good with that part, Max? So we come along, cruising. Yep, right with me. Why does it not go behind me? Who'd like to tackle it? Yeah. There we go. It has the same speed I do initially. We have to specify now. It has the same horizontal velocity as I do. We'll draw it. So here's me, a horizontal velocity. Here's the rag. Same horizontal velocity initially. Then what happens? What changes? Velocity? The vertical velocity, good. It gains a vertical velocity because it's accelerating due to gravity. So its overall velocity, of course, is like that. And so it'll do that little arc thing. It's going to head that way as this increases, the vertical, as it picks up speed vertically. So horizontally, it's going to go the same exact distance as me, or the plane, or the cart that we did that demo on. Again, because these don't change, so they go together horizontally. Yeah?
For the website homework, if we, sometimes you ask us like defend our answer.
Yes?
And if we want to go back and change that, is it possible when it's been submitted or no?
The defend your answer part? Yeah, as I've told you, that's to get you to try to, you know, I've emphasized to you, you learn better when you actually have to try to explain it. That's one of my ways of forcing you periodically to try to explain it. If you want to go change your answer, and you've already submitted it, it does treat it as a second submission. Thus, you are changing it. You can talk to me about that, because I can overwrite everything. But so in theory, yes, it would be docking you every time you resubmit. But the TA looks at every single one of those to make sure you're not just putting a bogus answer in. And so if your final answer makes sense, he can see that. You can contact us if you're really concerned about that. I would suggest on every single one, if you can't defend your answer, try to say it out loud to yourself or your roommate or your sibling. It's good practice. You'll find you feel dumb doing it until you actually try to do it, and then you realize, oh yeah, and then see the velocity was, oh wait, no. Is it velocity or acceleration? And then you realize where you need some help. You good, Max? How about others? Again, just another example where these determine how far it goes this way, and this one vertically. Yes? When you have to calculate it. I'm glad you asked. All right, let's say you're going 100 meters per second. I'm cruising. It wasn't me walking. This is fast. So that means the rag, or the package, or the ball is the same. So how far from when I released it in the horizontal direction, how far downrange will it be when it hits the ground? In 2 seconds. What are you thinking we should do? Right, so it's 100 meters per second. We're going to do that for 2 seconds. 200 meters. Yeah, so for 2 seconds, it will go 200 meters. That is, I'm getting crowded here. Distance is rate times time. The change in position is how fast you're going. That was also velocity was a change in position with time. It's just rearranged. That's essentially what we just did. The velocity, 100 meters per second for 2 seconds. 100 times 2, 200 meters. Let's give you a different one. Let's say this is 10 meters per second. And it falls for, we'll make it easy, 1 second. How far downstream, downrange, horizontally, will it be in 1 second? 10 meters. 10 meters a second. You do that for 1 meter, you've gone 10 meters. How far will it have fallen? 5 meters. How'd you get that? Whoops. We've done it enough now. Yeah, that thing. The vertical distance, the change in y, is 1/2 AT squared. 1/2 10 meters per second for a second is 5 meters. So in that first second of free fall, it falls 5 meters. Are we good with that? How fast will it be going after that second? Vertically. We've done this one several times by now too. What's the acceleration? Step through it, reason it through. 10 meters per second every second. So after 1 second, the acceleration is the change in velocity with time. So if it's 10 meters per second every second, it's going to change its velocity in 1 second. 10. It started at 0, so it gets up to 10 meters per second. Sorry, it's getting a little crowded now. So with that example, you can figure out how fast this would be too. And then you play this game. You know it'll do the same thing. It comes over this way. It'll do its arch still. You good with that? A follow-up question could be, okay, what is its combined speed now? Not just its horizontal and its vertical. After 1 second, what's its combined speed? We know it's going 10 meters per second horizontally, and we know it's going 10 meters per second vertically at that point. It's this length. Remember, it's a vector, so the size of that represents the magnitude. You can see it's going to be more than 10 because you have both contributing to it. And yeah, you play Pythagorean theorem. 10 squared plus 10 squared equals this final velocity squared, which would be the final velocity, the square root of 10 squared plus 10 squared. Or you can learn this, there's a few right triangles you can learn. If they're symmetric like that, it ends up 10 times the square root of 2. But yeah, I asked a clicker question on that. It'd be 14. I think the other one we've had was a 3, 4, 5 triangle. This was 3 and this was 4, then that's going to be 5, those ratios. But some simple ones like that are good to know. So it picks up speed. It doesn't change the horizontal, but it did change the vertical. So now its combined velocity is 14 meters per second. Is this helping? A few head nods, at least in the right direction. Okay. Other questions? Well, this is good. Think of these type of things. We'll do more of this Friday. I'm happy doing it now. So, as you go through the homework, when you learn the right answer, I hope you go back and look at the answer keys. Not just because, oh, I already know what the correct answer is. I did that when I answered the problems. But you can see my solutions. I mean, if it doesn't make sense to you with a why, there's it's one thing to know the correct answer. It's better to know why, because I won't ask the exact same questions on the test. Not always. All right. Well, today with relativity, I'm going to start with a little video. Help us get in the right frame of reference. And that's a lousy pun. There-ish.
From a different to us under different circumstances. At the moment, things look
You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. I'm into my frame of reference now.
My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the... Now I'm going to move in this direction. Behind. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the Earth as cart is moving at a constant velocity. The cart is pulled along by a string which is wound around this phonograph turntable, and that pulls it with a constant velocity.
So this is very similar to our cart where the ball shot up. They're dropping it.
When the cart passes this line, the ball is released, as you can see. I'm going to start the cart down at the end of the table so that by the time it gets to this point, I can be sure it's moving with a constant velocity. I want you to watch right here so that you will see the ball falling. I think you can see that the ball landed in exactly the same position that it did before, when Dr. Hume did the experiment with the cart fixed. But this time, the ball could not have fallen straight down. Let me show you why. The ball was released at that point. If it had fallen straight down, because the cart moves on and the time it takes to fall, it would have landed back here somewhere. But it didn't. If I were to do the experiment again, this time, I'm going to let you watch the motion through a slow motion camera, which is fixed here. If the cart moves by, the ball will fall, and you can watch in the slow motion camera. I'll show you this again. This time, there'll be a line on the film so that you can see the path. I think that you can see that the path of the ball is a parabola. But all of this has been in a frame of reference fixed to the Earth. All of this motion was in a frame of reference which was moving along with the cart. Frame of reference like that. Well, so that you can see what it looks like, I'm going to fix this slow motion camera so that it moves with the cart. Like this. I'm going to do the experiment again. And incidentally, I'll start it, and then I'm going to stand here so that when the ball falls, you will have something which is fixed as a reference point. In the moving frame of reference, I think you can see that the path of the ball is a vertical straight line. It looks exactly the same as it did before when Dr. Hume did the experiment with the cart fixed. If we were moving along in this frame of reference and we couldn't see the surroundings, then we wouldn't be able to tell by this experiment that we were moving at a constant velocity. As a matter of fact, we wouldn't be able to tell by any experiment that we were moving at a constant velocity. I'm going to do the experiment once more. And this time, I'm not going to stand here behind the ball as it falls so that you won't have any fixed reference frame. As far as you're concerned, that time, the cart wasn't necessarily moving at all. That time, when you couldn't see the background, then I think perhaps it was harder for you to realize that you were in a moving frame of reference. The important thing to realize here is that all frames of reference moving at constant velocity with respect to one another are equivalent.
I think that was fun. Fitting, too, that it follows right after your question. I'll show one more little clip on it, but I want to make sure we're all caught up to speed. The idea, you got the concept of frame of reference okay? Yeah, we've been doing relative motion at this point, but as we get into the special theory of relativity, it's all about that all motion's relative. There is no one preferred, fixed, absolute frame of reference. There's no main one. And that kind of threw people off. It all depends on which frame of reference you're in. Your frame of reference could be at rest compared to someone else's. Or you could be in the moving frame compared to someone else at rest. Or you could both be moving, but at different speeds relative to each other. And it changes what you observe. It changes your reality, in a sense. When you're riding along with the cart, it went straight down. You were in the moving frame of reference. That frame of reference was moving, going past, and you were fixed, it looked like it did a parabola, which is what we were discussing. We're in a fixed frame of reference talking about something moving along. So you have to consider the relative motion between things. About 3 more minutes here. 13:26. And then we'll see how this particularly plays in to relativity.
We are ever likely to run into this expression, U plus or minus V, is completely
Not
adequate.
this. Here you
So
go.
far, we've been talking about
Completely adequate.
moving at a constant
So far, we've been talking
to one another. Now I'm going to do the experiment with the drop to one another. Only this time, the cart will be accelerated relative to the Earth's frame. These weights will fall and give the cart a constant acceleration. I'll put the ball up, and then I will release it. The motion is very fast, and I want you to watch at the point where the ball is released from the fixed camera. Ready? I don't know whether you saw that or not, but the path of the ball was the same as it was before. Only this time it landed in a different spot. This is because the car kept on accelerating in this direction as the ball was falling. Now I'd like to let you see it again with the slow motion camera fixed onto the car.
Did you catch that? If the cart keeps on accelerating and picking up speed, but it released the ball's horizontal speed isn't changing. So this one's going faster and faster, accelerating, but this one's not. So they don't land at the same spot. Here's the slow-mo.
This time you saw the ball moving off to one side and not following down the vertical reference line as it did in the constant velocity case. But suppose you were in this accelerated frame of reference. How could you explain this motion? Gravity is the only force acting on this ball, so it should fall straight down. But if the law of inertia is to hold, there must be a force pushing sideways on the ball in this direction to cause it to deviate from the vertical path. But what kind of a force is it? It isn't a gravitational or an electric or a nuclear force. In fact, it isn't a force at all as we know one. So we're left to conclude that since there is no force that could be pushing in this direction on the ball, that the law of inertia just does not hold. This is a strange frame of reference. We call a frame of reference in which the law of inertia holds an inertial frame. The law of inertia holds in the Earth frame of reference, so it is an inertial frame. The cart moving at constant velocity relative to the Earth is an inertial frame, but the cart which is accelerated is not an inertial frame. Because the frame of reference that we're used to living in is one in which the law of inertia holds. When we go into a non-inertial frame, like the frame of the accelerated cart, our belief in the law of inertia is so strong that when we see an acceleration of the ball sideways, we think there is a force causing it. So we make up a fiction that there is a force. And sometimes we call this a fictitious force. Fictitious forces arise in accelerated frames of reference. The frame is accelerated in this direction, so you in the frame see an acceleration of the ball in this direction, and you say that there is a force causing it.
Questions? So the two frames of reference, an inertial reference frame means it's constant velocity. The relative motion is the speed isn't changing. A non-inertial reference frame is where it is changing and they're accelerating. The theory of special relativity, which Einstein is so famous for, has to do with inertial reference frames, constant velocity. That's chapter 35, and we're going to pursue that further now. Non-inertial, where things get even funnier, is where it's accelerating, and this theory of general relativity takes that into account. So if any of you want to start looking in that chapter, you can. So you know what it's talking about. I found people kind of get those confused. And some strange things can happen in non-inertial frames. So if you think the stuff we're getting ready to do is strange, start reading that. So this whole thing, I keep wanting to say it's kind of a perspective. But no, it's not really a perspective. It's really happening. It's just because you're in a different frame of reference. And there's no specific main one. Oops, I don't need the screens for a bit. Your book talks about two scientists, Michelson and Morley, and they were trying to set out that is not there some reference frame that is still? Isn't there? There's got to be one reference frame that's fixed. That's what they sought out to test. So they made an interferometer, which roughly they took some laser light and they shot it into a beam splitter. Basically, it lets some of the light go through and some of it reflect. And then it went off a mirror and came back. And this one went off a mirror and came back. And they recombined and they both came out this direction and they tried to detect it. The idea is if these go exactly the same path length difference, then they're waves that we're going to talk about. They're vibrating. We're exactly in phase, and they would cancel each other out. And they could see that here. But this is on the precision, the resolution of wavelengths of light. So it was very sensitive. Remember our pixels? You got your screen and high definition. It's more resolution because the pixels are smaller. We'll make the pixels the size of wavelengths of light, which is even smaller. So this was very accurate. And they did this over big distances, and they wanted to show that if one frame was fixed and the Earth's moving through it in one direction, then one side's going to change more than the other. And if it went this way, while this one was fixed, there should be a relative difference between the two path lengths. And so they set this up, and it's one of the most famous experiments where it failed. They did not ever see what they wanted to see, which kind of inversely proved that there was no fixed reference frame. There's no one preferred reference frame. They were trying to show it, and they couldn't. And people have since tried to test this and redo it, and nobody's been able to. That was what Einstein used to make his theory of special relativity. He based it on just two things, really. Two postulates. Number one, all laws of nature, this is in your book, are the same in all uniformly moving frames of reference. So inertial frames of reference. Constant velocity, uniform motion. Like in the thingy, the video, when it was non-inertial and was accelerating, whoa, it seemed to move this way. Where'd that force come from? We have to make up things. No, this is in inertial reference frames at constant velocity, where all the laws of nature are the same. So everything we've been learning in physics is true in any frame of reference, if it's inertial. Make sense? I like this one because it's logical. That means what we've been teaching you, it's true in any frame of reference, inertial frame of reference. So we don't have to learn new laws of physics as we think about different reference frames. And so far, no experiment has been able to reveal any of this absolute motion or preferred frame of reference. Number 2, his second postulate for the special theory of relativity. Summed up, the speed of light is constant. You've probably heard that before. The book writes it out. The speed of light in free space has the same measured value for all observers, regardless of the motion of the source or the motion of the observer. So no matter what inertial reference frame you're in, whether you're moving relative to me or I'm to you or both, all of us will get the same velocity for light. It'll have the exact same speed. It's a constant. Make sense? Or at least what it's stating. Well, given just those 2 postulates as the rest of the chapter, what are some consequences of that? And that's what Einstein reasoned together. A lot of people have came up with this. He was just poised to put this stuff together. Did lots of thought experiments. So you might find you have to think more about this stuff because it won't seem as natural. But it follows directly from both of these, and that's what I'm going to try to help you see. Questions so far? Okay. Well, let's, I got another video that I think will help. Simultaneity. Your book talks about simultaneity. That means 2 events that are simultaneous in one frame of reference. So if we see something happen at the exact same time, it need not be simultaneous in a different reference frame. We would think, no, we saw it the same, so it was the same. It's going to be the same for everybody. Not necessarily. Hopefully this video will help us understand that. It's only a couple minutes.
Imagine 2 observers, one seated in the center of a Imagine 2 observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the observer on the platform, he sees 2 bolts of light. Flashes of light from each strike reach him at the same time.
You see that? The little waves are traveling out. They're going the same speed. It's the speed of light. It's an equal distance, so they reach him at the same time.
So he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light.
That's just our distance equals rate times time. All laws are the same.
He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear.
Show that again.
Or the rear strike, because from his perspective on the platform, the train...
There, she's in the red chair there. This one struck, and then the wave went out at the same speed this wave goes out, but this one reaches the chair first.
The train is moving to meet the flash at the front and moving away from the flash at the rear. Flash from the front before the flash from the rear. But her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct?
Who do you think? Who's right? I know you don't know, but what's your gut say? Both of them? Doesn't that contradict? No, she's in an inertial, uniformly motion reference frame. Who else thinks both? They can both be right. Who thinks the person standing on the platform is right? On the train? All right, most of you are still confused because you're not playing. You're not voting. Well, here you go.
The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike. Einstein tells us that both are correct within their own frame of reference.
Good job.
This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
So that's one thing people had to grapple with. We're always like absolute truth, you know. One person has to be right. They both can't be right. Well, following both of these, they reason it out, and in their frame of reference, that makes sense, their conclusion. So they are both right. Yes, they disagree with each other, but they're in different reference frames. Given their reference frames, they're both absolutely correct. So, we've done this kind of game before. If the speed of light, which is represented by the letter C, the speed of light, that's a velocity. What does velocity equal? Distance over time. A change in distance over time. We're going to call that now, it's going to move through space and time at the same time. You've heard the term the fabric of spacetime, the spacetime continuum. Who's a Star Trek fan? Well, if you have that ratio, space over time, that's all velocity is. And for this fixed constant value of space over time, what if in this frame of reference over here, we cover more space? What's the only logical conclusion? If all these laws that we're learning are the same in all inertial reference frames, what do we conclude? Time must be different, and how would it be? Yeah, greater, a longer value. This you've probably heard about with special relativity, that time is dilated. Time stretches. Time can be longer in one reference frame than another. And you see how it follows from these? We're just using the laws we're used to. They all seem to hold in all inertial reference frames. And if the speed of light, we all get the same measurement, and they keep trying, and they still get the same measurement, then everybody has the same value. That's your saving grace with relativity. When you start thinking about this, you go home and you're starting to think, this is your constant. Space can change, time can change, but the ratio between them is the same for everybody. And that's how we get this. So if something's going to take longer, it can cover more distance, or vice versa. I have another animation for that. These help me a lot, so that's why I'm using them. All right. These are two frames of reference. If you're going a tenth the speed of light, just a tenth the speed of light, you can see the speed down here. We'll reset it. Do it again. These are light clocks. So on the top here, and from the spaceship's frame of reference, you're in the spaceship. You shine a light up, it bounces off a mirror and comes back down. Watch that one. Goes up, reflects off, back down, and you time how long that took. don't know if you can see it, it's kind of small. It says 4 nanoseconds. Well, if you're on the Earth watching the ship go by, so you're in a different frame of reference, but you're looking at that frame of reference, this is what you see. Down here at the bottom, you see the light, it bounces off the mirror and comes back down. Forget the values right now. That's just velocity times time. This distance is velocity times time. Maybe zoom that in a little. Value of c times t. Well, it went a longer distance up than this one did, didn't it? You can just see that represented. This is a shorter distance than this distance. And then it comes back down. Well, normally we would say, oh, well, those both happened in the same amount of time because the light went up and light came down. No, what is the same in both frames of reference? The speed of light. It's the velocity. This is our saving grace to get us to compare. So, down here, it travels through more space. It's a longer distance. That's like the left-hand side. Thus, it actually takes longer. For us, in the Earth frame of reference, watching the ship go by, we see that it takes longer amount of time to go up and down. We would disagree with the amount of time someone on the spaceship who is in that frame of reference moving with it would see. Let's go faster. Let's go 90% the speed of light. And it's more conspicuous. Those green beams of light are trying to go the same speed. One more time. They're going at the same rate, but you can clearly see that the bottom frame, it has to travel through more space, and it takes more time. And so the theory of relativity can actually predict that exact amount of difference in time that people will say. How much? If time's running more slowly for you on that spaceship, from my perspective and my frame of reference here on Earth, if you're in a spaceship, time would be going more slowly for you from my frame of reference. It wouldn't be for you on the spaceship because you're moving with it. And space would contract too, length contraction in the direction of motion. That's where we'll start back up next time.